What are logic microoperations? These are those types of microoperations that are performed on the contents of a register, and they are applied to the bits of the register. So it is a bit level thing. So if there are 4 bits in one register and 4 in another, and let us say the first register is A, the second is B, so A0 will have a operation with B0, A1 will have an operation with B1, A2 with B2, and A3 with B3, and these operations will be independent of each other. They will be performed at its own level. So this is called a logic microoperations, and we know about logic gates. Uh, this is very simple, that logic microoperations will be performed by the gates. They will be performed by the logic gates, and which we know about. There are gates like OR gate, AND gate, XOR, NAND, NOR, and others. These logic microoperations will be performed by using those gates. And here is a table. This is a truth table which is showing that we have 2 bits, right? Because logic microoperation is done on bits. So 1 bit of one register, another bit of another register. So if I had 2 bits, I will have 4 combinations, right? These 4 combinations 0 0 0 1 1 0 and 1 1, and I can perform various operations. So for example, if I perform one operation, can be one logic microoperation can be that whatever is the input, the output will always be 0. So this can be one microoperation. So whatever be the inputs, the output always will be 0. Similarly, there may be another microoperation that whatever is input, the output will be 1. Fine. This may be like this. This may be that function. Fine. And then there may be other functions. There may be an OR function which says that whenever all are zeros, it will be 0. Otherwise, it will always be 1. For example, this F7. This is an OR function. We may have an, for example, an AND function which says that whenever both are 1, it will be 1. Otherwise, it will be 0. Right? So we may have that function also. That is an AND function. So here we can see F1. 1 here, others are 0. So this way we can have some 16 functions which can be performed. Here in the table we have named them from F0 to F15. What will be these functions? We can just write them in terms of this symbolic language. So if the first function is whatever be the input, it will always be 0, the output. So that means the function will always be 0. F0 is always 0 irrespective of the input. So the micro operation will be F, this symbol and a 0 here. And what is this operation called? This is called clear, because we are clearing the contents of that register. That register, that bit of the register becomes 0. Right? And in the same way, if we look at this F1 operation, what is this operation? This is an AND operation, and symbolically is represented like this. F2 will be this thing, XY bar. You can confirm it from here. It will be XY bar, and which obviously can be written like this. Fine. This micro operation, and B bar, and F3. If you look at F3, F3 is 0 0 1 1, which is same as X. So F3 will be X, and that means it is just going to the output. Fine. So what will be the content of that? That will go to the output of that register. In the same way, F4 is X bar Y. If we look at F5, it is 0101, which is same as Y. Fine. So it will be B will be transferred, transfer B, meaning at the output we will find the contents of register B, and it doesn't depend on A. And then F6, if we see F6, this 0110, what is this? This is an XOR operation. Fine. We represent it like this by this symbol. F7 is just an OR operation. F8 is a NOR operation, invert of OR. F9 is an invert of XOR, which we call as exclusive NOR. F10 is Y bar. You can see it from truth table. Right? So Y bar implies that the complements of register B will be the contents of the bits of register B will be complemented. Fine. And F11, it will be X plus Y bar, like can be represented like this. F12 is X bar, that means the complement of the register A. F13 is X bar plus Y, which is like this, and F14 is not of an AND, so which we call as NAND. So do an AND, then do a not over the answer. And F15, we see this is all ones, so F15 is 1 irrespective of the input, so all ones. That means set all the bit to 1, all the bits of register will become 1. So these can be various logic microoperations. And we can see the circuit also. So here in this circuit, we see that we have taken just 4 out of the 16. We are doing 4 basic operations. So this is AND, OR, XOR, and this is NOT, complement. So if this is one stage, fine, this is one stage of the logic circuit, because we have 2 registers A and B. We are taking A of I and B of I. So for example, A of 0, B of 0, A of 1, B of 1, because it will be done at this level, at the logic level. And when we, for example, A of 0 and A of B of 0 is coming, we have to do an XOR. So this is a simple XOR circuit. The output here will be the XOR of A of I, sorry, OR of A of I and B of I. So it will be A of I plus B of I. Here, sorry, A of I dot B of I, and this will be A of I plus B of I, or this is A of I XOR B of I, and this will be the inverting of what? A of I, that is A of I bar. Now, since this whole circuit is creating 4 outputs, but at a time we obviously will require only 1. So it depends on the control unit. So now what we will do, this is very simple, that we should use a multiplexer here, because out of 4 things we need only 1 at a time. So use a multiplexer here. Then the control unit will decide. If the control unit says 0 0 here, then we will get an AND output. If it says 0 1, we will get an OR output. If it says 1 0, we will get an XOR output. And if it says 1 1, we will get a NOT output of A. So if we have 4 bits in that thing, in A there are 4 bits, in B there are 4 bits, then it will be 4 times this thing, and we will get those 4 outputs here. So this stage will be 4 times for A of 0, then A of 1, A of 2, and A of 3. So we will get 4 outputs. That 4 outputs will be the contents of output register. And this whole functioning can also be summarized in a function table where s of 1 and s of 0 will decide what will be the output. Fine. Let us see some of the applications of logic microoperations. And let us suppose that we have two registers. Register A contains this number, 4-bit binary number 0011, and let us say B contains 0101. Right? And let us see the first operation, that is selective set. What is a selective set operation? It is an operation where all the bits of a certain register are set, that is, they are put to 1 with respect to ones in B. So if I want to set all bits in this register A to 1, but which bits? Those bits where there is a 1 in B. This is called a selective set. So it sets to 1 the bits in register A where there are corresponding ones in register B. So if this is A, this is B, fine. So we have to operate on A. We have to do selective setting of A using B. So this is the operand. So wherever there is 1 in B, A is to be set. So if this is here, we have 1. So this A here will become 1. Again, here B is 1. This A will become 1. Here in this example, it is already 1. At other places, A will remain as such. So here A was 0. Here it was 1. So it will remain 0 and 1. And so this is selective set. Now, if we see, I have taken this example deliberately because if we see A and B, we have all 4 combinations. Here we have 0 0, 0 1, 1 0, and 1 1. So all 4 combinations of 2 bits are there. And if we check for 0 0, it is giving 0. For 0 1, it is 1. For 1 0, it is 1. For 1 1, it is 1. So we know that this is the truth table of logic OR. So that means we can use the OR logic microoperation to perform selective set of any register. Another is selective clear. So selective clear means it clears to 0 the bits in A where there are corresponding ones in B. Wherever there is 1 in B, the corresponding bit in A is put to 0. So if there is 0 in B, nothing happens, 0 remains 0. If there is 1 in B, then this bit is kept as 0. Fine. So 0, this 1 remains as such, and if it is 1, this A bit becomes 0. And if we see this truth table, from this truth table we can calculate that this is this logic A and B bar. So this answer is, when we operate on these two inputs, it is this logic. So this again, we know this is already a logic micro operation that we have. Of the 16 logic micro operations, this is one, and so that thing can be used to do the selective clear job. There is another called selective complement. Means that bits in A are complemented, are inverted wherever there is 1 in B. So this is A, this is B. If B is 0, nothing happens. This 0 remains as such. But if B is 1, A bit is inverted. So this 0 becomes 1. If this is 0, nothing happens. And if this is 1, this bit is inverted. So this is it. And if we look at this thing, the truth table of this 0 0 0, 0 1 1, 1 0 1, 1 1 0. This is exclusive OR. So this is same as exclusive OR. So using logic micro operation of exclusive OR, we can do selective complement. The fourth operation is mask. This operation clears to 0 the bits in A wherever there is 0 in B. So it is clearing it is a clear thing. It is same as the selective clear, but the condition is different, that whenever there is 0 in B, the bits of A are to be cleared. So here, whenever there is 0 in B, this is to be cleared. Whenever there is 0 in B, this is to be cleared. Other things remain as such. And if we look at this thing, this is an AND operation. So whenever we want to do masking, we can use the AND logic micro operation. Fifth one is insert. So this operation is used whenever we want to insert certain bits into a number. So for example, we have an 8-bit binary number and we want to change certain number of bits in that number. We want to insert some new different bits there. So this operation is used to add a new value into a group of bits, but this is not a single step operation. Here it is done in 2 steps. First, we do the masking thing. Those bits which we have to change, we first mask them. That is, we make them 0, and we already know how to mask. Then after making them 0 by masking, we do an OR operation and with the thing that we have to insert. So let us say we have a number, this is a number A, 8-bit number, and first of all we had to do masking. Let us suppose that these first four bits have to be changed to 1001. So the problem at hand is that this is a number in a register. We have to change the first 4 bits to 1001. For that, first we will do masking. That is, at these 4 places we will take another register, put 4 zeros here, remaining ones. And when we do masking, we know that wherever there is 0 in B, A will become 0. So this A will become 0 0 0 0 1 0 1 0. Fine. This we know that can be done using an logic AND operation. Fine. Now we have to insert 1001. So take this number, this output number, and do the insertion thing. How to do insertion? Now take that number which we have to insert in B. So 1001 is to be inserted. Put it 1001 here and remaining zeros. Just do an OR of these things. And we know when we do an OR of these things, these 4 zeros will be replaced by 1001 and the remaining will remain as such 1010. And this is ORing. So insertion can be done first by masking, then by ORing. And the 6th operation is clear. So what is clear operation? This operation compares 2 words in A and B, and it will check whether the contents of that register are. It will be helpful in checking whether the contents of 2 registers are same or not. And if the contents of A and B are exactly same, it will produce an all 0 result. Right? It will be an all 0 result if the 2 values are same. So it can be used to clear A, that is to make all bits in A 0, and it can also be used to check 2 numbers whether both are equal or not. Because if the answer is 0, they are equal. If the answer is not 0, they are unequal. So for example, I have a number this 0011 in A, and in B also we have the same number. If we done an operation, it produces all zeros. And if we check this thing, what is this? This is logic XOR. So logic micro operation exclusive OR can be used for clearing purpose.